Okay, so we are recording now. So again, I'll make that comment that I had made. In section 5.2, we learned about the definite integral. The definite integral, we use this kind of curvy S symbol to denote a definite integral. And then we have a bottom limit of A, x equals A, and a top limit of B of f of x dx. This is our definite integral. And the geometric interpretation of that definite integral is it's the net area of a function, the net area between a function and the x-axis from your limits x equals a to x equals b. Okay, so pictorially, and I know you're going to copy the example down, but I'm just going to talk about this for a moment here to kind of refresh your minds. So you could have a function, you could have a function like this. Okay. Let me see here. Let me extend that x-axis a little bit more. Make this look a little bit nicer. Just kind of writing it down. This is the x-axis, right? And you have limits here. This is x equals a. This is x equals b. Okay, and this definite integral here represents the sum of the areas. Okay, the sum of your areas between this function in red, this function f of x, and the x-axis. Okay, that's what it represents. And of course, we know that, like if we focus on this, why is one bold? This one here, I don't mean this one here to be bold. Okay, I don't mean it to be bold, John, in the example. It's just a one, number one. So in this problem here, in this little picture, this area here that I'm delineating right here, would this be positive or negative area? That area. Would that represent positive? Okay, good, Ian, good, Betsua, good, Joe. That's positive area. So that area is positive. Okay. Well, what about this area here? Bounded between the function f of x and the x-axis, but the area is below the x-axis. Good, everybody. That's negative area. That's negative area. Very good. So that area is negative. And then you have area here. Okay. And that area is above the x-axis. Okay, so that area would be positive area. Okay, so what you're doing when you compute a definite integral is you're effectively adding up the positive areas and the negative areas and getting a net total of the areas. Okay. And right now, what you've learned is that the way you can find the exact value of this definite integral is to compute the limit of a Riemann sum. So like in section 5.1, you're introduced in approximating the area under a curve by using like left endpoints and right endpoints, adding up areas of rectangles. And then that brings you into section 5.2, where you have the Riemann sum. And we've actually done two problems. Actually, one was actually from section 5.1, where you computed the limit of a Riemann sum and got the area underneath the function. And in section 5.2, we did another problem like that. So it's important to be able to also look at a limit of a Riemann sum like you have here, and then state what the definite integral is. Okay, so it's like we're going backwards. Usually we have the function and we write the Riemann sum, but now we're giving a Riemann sum in this problem, and we want to write it as a definite integral. So think for a moment what would the definite integral be for this particular Riemann sum. Just think for a moment, okay, and then we'll go over the solution. All right, everybody, so let me get to the solution here. I think let's see if you have the right function in mind. So, okay, in our solution, what I've done is well, let me go back here. Okay, let me go back. So this is our limit here. And what I'm doing is the 1 over n, we can treat like a constant with regards to the summation, because the summation goes from I equals 1 to n, but it's the I value that's changing. It just ends up at the first value of I is a 1, and the last value of I in the summation is an n. So with regards to the sum, 1 over n can be brought inside the sum. All right. So are there any questions on this first step here? All right. Well, then let's proceed on. So remember what the Riemann sum is. The Riemann sum is the sum is the well, I mean, let me just put it off to the side here. The Riemann sum, just the Riemann sum itself, is the summation starting at I equals 1. Sorry, hold on. Starting at I equals 1, going to n, ending up at I equals n, of f of xi times delta x. Okay, and so you're, you know, again, what you're doing is you're taking, you know, you have some function f here, okay, between the limits of a and b, and you're adding up areas of rectangles. Hold on. You're adding up areas of rectangles, and how you choose the rectangles depends on whether you're using the left endpoints to determine the height of the rectangle in each subinterval, or the right endpoints, or the midpoints. Okay, and every rectangle, okay, I'm trying to do this nice, best I can, but it's a little hard. Man, this is not easy. Okay, that'll work. Every rectangle has width delta x. Okay, so that's, I'm pointing this out because, you know, here we have a sum of f of xi times delta x. So based on what we have above here, well, the delta x would have to go with the 1 over n. Okay, because delta x is it's the width of all the subintervals, and that doesn't change. So that 1 over n would have to go with delta x. The f of xi would have to go with this part of the expression because there's an I in that expression. So f of xi goes with 1 over 1 plus I over n squared. Okay, so far are we good up to this step? Please let me know if you have any questions. Okay, one moment here. One moment, everybody. Be right with you here. I'm just deactivating the assignments. We don't want anybody working on the exam or anything during the lecture, right? And I particularly think about students that maybe don't come to class. I don't want them working on the exam while you're here in class. That's not fair to you, you know. Let me see, there was a question here. Let's see, Sebastian says, how do we know A, good question, how do we know A and B are 1 and 0? Couldn't there be any other number with a difference of 1? Well, let's talk about that, Sebastian. Excellent question. So how is delta x defined? Well, delta x, remember, is the width of each subinterval. So you have n subintervals, and you have a minus b divided by n. That's how delta x is defined. Actually, I have that wrong. Hold on, I have that wrong, class. It should not be a minus b. It should be b minus a. Let me fix that right now. It's b minus a divided by n. Well, the delta x is equal to 1 over n. So the n is in the denominator, 1 is in the numerator. Well, the only way you can, the way you could have a 1 is having 1 minus 0. But I want to be a little bit careful. You might say, well, how do you know it isn't, how do you know in the numerator you don't have like 3 minus 2? 3 minus 2 equals 1. Why am I choosing 1 minus 0? Well, it has to do with this part here where the function is. If you, like x sub I, okay, x, I want to be a little bit careful here. I don't want to have too much going on here. Erase, erase, erase. But, okay, we could, x sub I is equal to a plus I times delta x. Okay, it equals a plus I times delta x. That's the like how you pick your points in each subinterval. That will determine then the height of the rectangle in each subinterval. If we were to use the right hand, if we were to use the right endpoints, then x sub I would equal a plus I times delta x. Well, a, if we let a be 0, delta x is I over n, you get I over n. So what I'm trying to do is justify this I over n right here. Trying to justify that. It comes from somewhere, right? It comes from somewhere. Well, it comes from the x sub I. X sub I is equal to I divided by n. That's what x sub I equals, I divided by n. So the only way x sub I would equal I divided by n is if the a were equal to 0. Because delta x, you know, is 1 over n. You know delta x is 1 over n from right here. So I times 1 over n is I over n, so you have to then, a has to be equal to 0. And so then, since a is 0, b has to be 1. And so your definite integral is from 0 to 1 of 1 over 1 plus x squared dx. Okay. Sebastian says, would we have a different question where a and b are different? Well, a and b are different. A is equal to 0 and b is equal to 1. But you could have a different. I'll tell you what. It's actually, let me show you an example in the book. It's actually a very good question Sebastian has here. Let me show you an example in the book to help you see something else here. Okay. May I? Well, are there any questions on this? May I go to the ebook? All right, one moment. Let me get to the ebook here. One moment. I'm just going to get the section and I'll get right back here. One moment. Okay, okay, everybody's good? All right, so one moment. Let me bring up the ebook. Here, I'm going to be looking at example 3. Here. Okay, let me stop sharing here. So this is the final answer right here. And it's always good to look at a variety of examples. So we're looking at section 5.2, example 3. Okay, and in this problem, they want you to set up an expression for the definite integral as a limit of sums. The definite integral goes from 1 to 3 ex dx. Okay, so what they do is here, a equals 1 and b equals 3, right? And so delta x, by definition, is b minus a over n. So you get, that's 2 over n. So far, so good? So like if you have an interval, you know, from like the intervals from 1 to 3. So if you decide, well, I'm going to have 4 subintervals from 1 to 3, how wide would each subinterval be? Okay, meaning if you were going to use 4 rectangles to approximate the area under the curve, from 1 to 3, if you divide that into 4 subintervals, each subinterval is going to be a half, right? But the way you can quickly, I just did that in my head, but the way you can quickly get that is take, you know, 3 minus 1, which is 2, and divide by n, 4, which is a half. So this delta x formula always works for no matter how many subintervals you have. Now your initial value, x naught, is equal to 1. That equals the a. x1 is going to be 1 plus 1 times 2 over n. x2, it would be 1 plus 2 times 2 over n. x3 would be 1 plus 3 times 2 over n. And I think you get the general idea. X of I would equal 1 plus I times 2 over n. So they write I times 2 over n as 2I over n. And they're using here right endpoints. That's what they're using. They're using right endpoints to determine the heights of the rectangles. And so therefore, the definite integral from 1 to 3 of e to the x dx would be the limit as n approaches infinity of the function evaluated, f of xi, which would be f of 1 plus 2i over n, times delta x. And delta x is just 2 over n. And so e to the x, well, e to the 1 plus 2i over n is what you see right there. It's right here. I have to highlight the whole thing, but you see in the bottom, the yellow that I've highlighted, the bottom piece there, you have e to the power 1 plus 2i over n. And then the 2 over n in the summation, they brought it out in front of the summation. Okay, and so hopefully that is helpful. Okay. All right. Are there any questions? Well, no. 2 over n. You can't, Ian. You can't take out the 2 over n in front of the limit because the limit is n goes to infinity. You can bring the 2 over n like they did out in front of the summation, but you can't bring it out. You can't bring it out any further. But if you notice, this form is like this problem is like the 2. Actually, no, you do not have to bring 2 over n out in front of the summation, but they do. But you don't have to. I prefer actually to leave it in there. But you know, if you get a problem where 2 over n or whatever 1 over n is out in front of the summation, you can just bring it back in, like we did in the example we just looked at. Okay, so this is like going the other direction of the example we just looked at. Example 3 is like going in the other direction. And of course, the issue becomes then, how can we compute this definite integral? How can we compute it? Well, they mention about using a computer algebra system. Well, you know, we're not going to be doing that. But what they're because you know we're working out the Riemann sums by hand, right? So like remember, you know, of course, you want to work them out by hand, like I showed you in the two examples that I already did, and they're in the recordings for sections 5.1 and 5.1 and 5.2. But the thing is, this definite integral, when you write it as the limit as n goes to infinity of 2 over n times the summation I equals 1 to n times e to the power of 1 plus 2I over n. Okay, sure, we have that, but how do you compute that? How do you compute that? So the problems we looked at, remember the two problems where we actually computed we found an expression for the Riemann sums and then took the limit of those Riemann sums so we could compute the definite integrals. The two examples we did, we relied on these formulas here, formulas 5, 6, and 7. Okay, we relied on those formulas to write the Riemann sum as a function of n. You know, we have to you know, find an expression for the summations, for the sum, and or summations. Well, in example 2, you can't, or sorry, in example 3, you can't do that easily here. And so even though in sections 5.1 and 5.2, for the problems you're going to have where you have to compute find the limit of the Riemann sums, you can rewrite the Riemann sums using formulas 5, 6, and 7, those summation formulas. But in general, it's not going to work in general because, like for this problem here, this Riemann sum, you're not going to be able to find that using formulas 5, 6, and 7, and it's not easy to find. But you'll be able to find, for instance, on Monday's class, I'm going to show you a way in which you can compute a definite integral without using a Riemann sum. And like for this problem here, they actually show that the definite integral from 1 to 3 e to the x dx, okay, they actually, and by the way, that's this area here. That's this area, right, the blue area that they're showing underneath the exponential function e to the x from 1 to 3. You'll be able to see compute that area as being e cubed minus e. And like they say, we're going to learn a much easier method for evaluation of integrals in the next section. Okay, so nevertheless, for like 5.2 in your homework, you have a couple of problems where you do have to use a Riemann sum, and you know, simplify it and take the limit, and you know, simplify it using those formulas 5, 6, or 7 and work it out. But I'm only doing it for a few problems, you know, just so you appreciate the process. It's important to understand the process. So Sebastian, does that help you feel a little more comfortable with? Okay, good. And also in you're welcome. Also, like in section 5.2, you know, they talk about using geometry to evaluate integrals, and we talked about this a little bit. So, like for instance, the integral from 0 to 1 of the square root of 1 minus x squared dx. Well, that function, square root of 1 minus x squared, can be thought of as a function that bounds a circle of radius 1 in the first quadrant. So if you're going to find this definite integral, you don't need a Riemann sum. You just need to know, hey, you know, the area I'm looking for is 1/4 of the area of a circle with radius 1, and so that's going to be 1/4 pi times 1 squared. and you get pi over 4. Okay, so you don't need anything, you don't need Riemann sums to compute that integral, right? And also for the second problem where you have the integral from 0 to 3 of x minus 1 dx, okay, for that problem, all right, there, all you need to do is graph y equals x minus 1, and then your limits are from 0 to 3. And so in figure 10 here, you're going to have a positive area, A1, that goes from 1 to 3, and a negative area, A2, that goes from 0 to 1. But areas 1 and 2 are just triangles, and you can find the areas of triangles, you know, 1/2 base times height. And so this is, you know, this is how they do that. But of course, the second area is negative. You know, you're in section 5.2. You're dealing with fairly simple definite integrals. Okay, are there any questions on that? Okay. All right, Joe's good. Very good. All right. So now, remember we talked last time. We talked last time about some rules for definite integrals. Okay, we talked about some rules. This was one of the rules. If you have the integral from b to a of f of x dx, it equals negative the integral from a to b of f of x dx. All right, and also, if you have where a equals b, okay, the integral would equal, that integral would equal 0. In other words, if your top, I think this is kind of bad notation. If your top and bottom limits are the same, then you don't have any area to compute. And so the definite integral is equal to 0. There's no area. That's really what we're talking about. And then you have some properties here. You have some properties of the integral, these 4 properties that are very commonly used. What we're going to do is we're going to do another example here. And I want you to have these properties in your ebook. This is in your ebook, these properties. They come before example 6. Keep these properties handy because we're going to be using them. Okay. But remember, the properties, why are the 4 properties, why are they the way they are? Well, remember, any properties that are true for summations are true for definite integrals. So, like, for instance, if we look at towards the beginning of section 5.2, okay, they have here some properties for summations. Property 9, you know, if you have a constant inside a summation, you can bring the constant out in front of the summation. If you have the sum of summation of AI plus BI, that's just, you can add those summations separately. You can add those differently. And similarly, if you have the summation of AI minus BI, that's just the sum of AI minus the sum of BI. So these are sort of natural properties that you maybe have encountered before in pre-calculus. A few of you told me you had, but because we looked at these a little bit in the last class. But even if you haven't, they're sort of natural, these properties. Well, the properties for definite integrals, okay, let me just get it here. These 4 properties for definite integrals, well, the first property is just, you know, we talked about that, but properties 2, 3, and 4, those are just analogous to the summation properties that I showed you, that are there just before example 2 in the textbook. Okay, so that being said, let's go ahead and do another example here. Let me stop sharing this. Let me bring this example up. Okay. Okay, so this problem, here's the definite integral, and I'm going to give you a chance to copy this. Here's the definite integral. Okay, and we want to find its value. We want to find a number, actually. And, you know, the 2x is there, the 5 is there. But f of x, what's that? Well, this is f of x right here. This is the f of x function right here. And the f of x function here has regions A, B, and C bounded by the graph of the function and the x-axis, and each of those regions has area 3. Okay, so let me give you a moment to copy this down, and then we'll talk about the solution. And the purpose of this example is to help reinforce those properties of integrals that I just showed you. Okay, so I know you're still copying. It takes a little while to copy that picture. You want to copy it nice. What does that curve remind you of, by the way, this function f of x that you see here? What is that in the picture? What does that curve sort of remind you of. Yeah, a sine. Good, Nicholas. Good, Ian. Good, Joe. Good. It's a sinusoidal curve. And what's the period of the sinusoidal curve? What's the period? How long does it take for the, like, what's the, that's right, 4. Good, because it takes a distance of 4 for it to do one cycle. And of course, you learned in pre-calculus and trig how to find functions, you know, if you have a sine curve. And I mean, the normal period for the sine wave is 2 pi. This sine wave has a period of 4. So you could come up with the equation if you needed to for the function, but you don't need to do that. All right? You don't need to do that. Okay, give you a couple more minutes to copy this down. Okay, so, well, I mean, here's our definite integral. And it's the definite integral of the sum of 3 functions. F of x, okay, and 2x, and 5. Okay. Intuitively, what do you want to do with this integral? How do you approach this problem? You have the integral of the sum of 3 functions, or the definite integral of the sum of 3 functions. Let me show you something here. One moment. Hold on. All right, Kelvin says separate them. That's exactly right, Kelvin. Exactly right. We want to separate these. We want to separate out the integral. And may I go to the ebook? Does everybody have the example copied okay? Okay, all right. So if I go to the ebook here, okay, and go back here to the properties, these 4 properties, 1, 2, 3, and 4, which property am I going to use? Property 1, 2, 3, or 4? Good, good. Good, Kelvin. Good, Ian. We're using the second property. And, you know, the sum of 2 second property says the integral of a sum is the sum of the integrals. Well, it would follow if the integral, if you had the integral of the sum of three functions, that would be the sum of three integrals. Okay, so we're going to use property 2. And okay, well, let's go ahead and get that then. One moment. Okay, so by integral properties, the integral of the sum of these functions is the sum of the integrals. Okay, the sum of the integrals. That's the first thing you need to do. And you notice the limits, the 2 and the -4, I'm not sloppy in my notation. I carry those limits. And I would expect you, you know, on the final exam, you'll have maybe a problem like this, you will want to be just as neat, you know, because it means something. If you don't have limits, on your integral, then you don't have a definite integral anymore. You have what's called an indefinite integral. An indefinite integral. All right, and we'll learn a little bit about that on Monday. But okay, now the 2x here. What can I do with that 2? Can I do something with that 2 in front there? Good, Sebastian. Factor it out of the integral. Factor it out of the integral. Okay. That corresponds to the third property of the integrals. So I'm going to do that. I'm going to do that. One moment here. Okay. And that gets me down to here. Now what I need to do is I need to compute these separately. So what I'll do, and by the way, in the beginning, I called the integral I. I called it I, and that's not uncommon to when you have a definite integral, you set it equal to the capital I. So my capital I integral then would just be equal to this, to the I sub 1, the first integral here, plus 2 times the second integral. I call that I2, right? So this is I1, plus 2 times I2, plus I3. Okay, and that gets us here. That gets us here. But now, of course, we have the task of computing these three integrals separately. Are there any questions so far? Okay, all right. Well, so this first integral here, we're going to have to rely on the picture. So what I want to do is I want to go back to the picture. Okay, here's the picture of my function f. And can we figure out, based on the picture, hold on, got that wrong. Here's the function. And what we're looking for we're looking for this definite integral here. And we're told that each of the regions, A, B, C, has area 3. Okay, so what I'm going to do, I'm going to write something in here. Okay, I'm going to write 3 here. I'm going to write a 3 here. And I'm going to write a 3 here. Is that right? Ah, good. The two, that's right. And thank you, Rodrigo. Ian and Kelvin are saying that these two here, the areas that fall under the x-axis need to be negative. So I'm going to have a -3 for A area, a -3 area for C, and then a +3 area for B. So what would, I mean, how am I going to find this definite integral? Can somebody chat out how I would find it? Add them up. That's right. Add them up and you're going to get 3. Well, I'm sorry, you're going to get -3 plus 3 plus -3. And so the net area is going to be -3. Okay, and I actually have this on the formal page on our solution, but so I'll go to that. But are there any questions on that? Any questions? Okay, well, if we're good, then let's go here. All right, so what I just did is demonstrated here. Okay, -3 plus 3 plus -3 for areas A, B, and C. So I mean, technically, yes. If you think about like area not regarding this positive or negative, those regions have each area 3. But the definite integral involves it's the net area. So you have to consider areas below the x-axis as being negative areas, and areas above the x-axis as being positive areas. Now for the second one here, the second integral I sub 2, well, I'm just going to draw the y equals x function from -4 to 2. And, you know, I have 2 areas here, right? I have 2 areas. I have an A1 area. Maybe I'll put it in red. I have an A1 area. And I have an A2 area. Well, the A1 area is negative, and the area of a triangle is 1/2 base times height. So for the A1 area, the base is 4, and the height is 4. And I would expect to see this kind of work on the final exam. I don't want to see, if it's a section 5.2 question, okay? I don't, would not want to see just an answer, okay? All right, so this gets us our area for A1. And then for the second area, the base is 2 and the height's 2. And that area is above the x-axis. How many think this is kind of cool? I think it's kind of fun, don't you? All right, who can get down with this? Sebastian can get down with it. Kelvin can get down with it. Nicholas, sure. I mean, you're learning really good stuff here, you know. All right, Rodrigo likes it. Uh-oh, Betsu's a little nervous. All right, good, good. And Joe can get down with it. I like it. I like it. So, okay. Well, all right. So the second area is -6. Okay. And now for the, so you know, we had to draw the function x, right? From -4 to 2. Now for the third one, we have the third integral. Our function is 5. So I draw y equals 5 here. Okay, from x equals -4 to x equals 2. And unless I'm wrong, that I'm looking for the area of a rectangle, right? And the area of a rectangle is base times height. So the height is 5. And the length of the base is 6. Okay, and so that integral is going to be 30. Let me give you a moment to copy it down, all down here. All right, and of course we're not done yet. We have to now compute the entire integral using the entire definite integral, using, you know, the definite integral I, because remember I was equal to what was it? It was I1 plus 2I2 plus I3. So we have just one more step to do. May I go to the next page? Are there any questions? All right. Okay, thank you, Nicholas. Thank you, John. Everybody's good? Okay, thank you, Betsua. Okay, thank you, Zoe. All right, thank you. Well, then, you know, our final answer then is going to be 15 for our definite integral. Because remember, we have I1, right, plus 2 times I2. This is I2. That's that definite integral. Plus I3. Okay, and that gets you 15. All right, are there any questions? All right, well, if there are no questions, I'll stop the recording here.